Okay, good evening, everyone. I'm Arvind Heda from presently working with InfoEdge, and for past few years, I've been involved in building data platforms. So based on that, we've created platform for a couple of domains, and when we created data platform, our vision was to get not only the data in one place, but to pull in all the processing, which includes like whatever interactions a business needs to have with data, whether it be a query for reporting, whether it would be an ad hoc query, whether it would be a real-time interaction for the app, or whether it's some model learning exercise on the data. Want to get it all in one place, and so that it becomes the single point of truth for everyone in the organization. While doing this, we picked up Spark as the core for the platform. We picked it up for all the components in the platform. And based on our experience, what we observed is we were able to scale all the components of the platform to the level that we were looking for. But one area where we faced some challenges was the interactive query part. Because we want the interactive query part to be there as well. And that's an area where we face some challenges while using it directly. And then we started with the project Indicium, and that's what we'll be focusing on today, how we were able to scale interactive queries on top of it. This is just a quick sequence what we'll cover in this session. So we'll go through the unified data platform on Spark. We'll cover the stack very briefly because we'll not dive deep on the platform side, but specifically on the last part, which is the interactive queries. What were the challenges that we were facing there, and how we put together different components. We picked up most of the component from the open source community, as well as we built some logic on top of it. And those are the two phases of Indicium, which is part one, where we pulled out some components and created a model where we were able to scale the interactive queries. But then in phase two, we added the logic on top of it to really make it scalable to the level where we were looking for. So quickly going to the unified data platform part. I would again put a disclaimer here. Unified is an overloaded term, and different people are using it for different purposes. But what we are saying, unified data platform here is, it's not only getting all the data in one place. It also includes to pull all the processing on the data, which is related to data, onto that single source. So what we were trying to do was not only the data for reporting, not only data for BI, all your machine learning tools, but even some of the real-time interactions, as well as if you are looking for interactive query, those should be driven from the same source. And the reason was we wanted to avoid creating and maintaining a second source of data. Right, so it of course needed a common data lake for storing the transactional data, behavioral data, or computed data. So we were keeping all three sources together, and the reason was the transactional data, behavioral data, and computed data. Any of this data could be used when you end up doing ad hoc analysis or interactive queries on data. And because since we were discouraging using any other source for any interaction with respect to data, so we need to keep all this data together. Second is we want to drive all the decisions, recommendations, reporting, analysis from the same store. This was again just to ensure that every decision, every recommendations, all the reporting remain consistent, and we were totally focused on keeping the data in just a single copy of data. While data is being collected into various databases, traditional databases, so it was a heterogeneous architecture, so data was coming from RDBMS, it was coming from Mongo and various other sources, but then finally every data landed up into the common source. And this was a single source from which we were pushing all the decisions. So we had a real-time edge on top of this, which was used by the application to make real-time decisions. Any model building or BI tools, which does scheduled reporting, were also driven from the same data, as well as the ad hoc and the interactive query part. Now, for this data platform, what was needed, right? We were requiring scale both to store and query this data. The scale that we were looking for was in the range of 100 to 200 terabytes of data that we were trying with. In our case, it was about 10,000 scheduled queries or scheduled jobs that were scheduled as a daily run on this data. Plus, there was a team of 80 to 100 data analysts or data scientists for which we want to enable ad hoc query or interactive query on this data source. So that was the scale that we were looking to support with. Concurrency was another thing. Again, when we look at concurrency, concurrency from the application standpoint was always designed for and comes right in the beginning of the design. But when we look concurrency from user interaction, right, the ad hoc users who are just making interactive queries for data analysis, how to support them, how to support concurrent number of users and their ad hoc queries on this. And ad hoc drill down was another example where for any BI tool, if you want to do a drill down queries, you need to support that as well in a concurrent manner. One another thing with the ad hoc drill down queries is because when you start doing ad hoc drill down queries, you may end up reaching to any transactional data. So you may start with the computed data, but then you may need to go to a fact level. And that's where we wanted to keep all the data to transactional behavior and computed data into this single source. So this was the high-level model that we ended up with. Or I will say we'll start it up with. We'll go to the Indicium phase 1 and phase 2 where you'll see some changes there. So this was a standard this was a standard platform architecture where you have data pipeline. The lower part data pipeline is there, which is where we have the Kafka and RDBMS as a source. You have a data collection service, which pulls this data in real time or some of the data in near real time and pushes it into a common storage, which was HDFS or S3. We have a real-time lookup edge, which we keep updated as soon as data is flowing. And this real-time edge is used for real-time decisioning from the application side. And now, coming on the upper part, which is this one, where we have this compute layer. This was a common compute layer associated with the platform, and this common compute layer used to take care of all compute requirements, whether these are scheduled compute jobs, these are ad hoc compute jobs, whether these are scheduled queries or ad hoc interactive queries. What we did purposefully is we separated the Spark context, or you can say the resources, for the scheduled jobs and the interactive jobs. And the reason was we didn't want our interactive jobs to just get mingled with the scheduled jobs or just get into the same queue, where some of the scheduled jobs could be really complex and running for hours and so on. So we created two sets of Spark context and had dedicated resources for it. Overall, they were still sharing the common compute layer. And we were using the dynamic pooling capabilities to get some fraction of from each other as and when possible. So there's a quick rundown of what things we use for various components. For data persistence, we used, we were reading it from Kafka, but then persisting it in Parquet format over S3 and HDFS. We had Spark modules there to read it periodically from there. Data transformations, again, from the Kafka layer, we had various transformations or enrichment layer. These were, again, Spark jobs running on top, reading from the Kafka and then pushing it to another queue. Algorithmic access, again, once the data is persisted on HDFS and S3, what we enabled was we provided a dedicated queue for someone to submit the job with a data access layer. That data access layer in which we overridden the SQL context part. So we were able to provide them the data that they were looking for from the underlying persistence that we had. Because the underlying storage structure, we were having our own. It was like the folder structure and the hierarchy that we were maintaining on our end. Decision making, the real-time edge, which was really an in-memory cache, which we were used to do real-time decisioning for any application-related real-time decisioning task. It has its own APIs, and it has updated profiles with it. And then reporting BI ad hoc tools were again connected to the same compute layer, and they were firing their scheduled queries through the same scheduled job queue. Now, the interactive queries, or the area where we faced some challenges, there were scaling challenges while using directly the Spark SQL, because we had the dedicated resource pool, we had Spark context there, but interactive queries are not something which are predictable, right? Because there were 100 users, they can fire their queries, and these queries are not something which you can predict for. You can predict for, and you can create your systems for application-based integrations, because you know what type of query would come and what frequency it would come in. Interactive queries, you don't know what someone would fire. Someone can fire a bad query, someone can fire a big query, and how it would hog up your resources. And then if someone has to run really simple query, then what would it take? How would he get the resources? How to prioritize resources between these two? So that's where we were facing issues of how to scale the system. So if you see the top compute layer, actually it was not a real-time queries. While for interactive queries, people expect that the responses should come in real time. When they fire a query, that query should be executing. It may not come like the very next second, but it should be executing, and it should give them real-time execution and give them the response. But in reality, when we push it on the compute layer, it was a FIFO scheduling. First in, first out, you give your query, it would be in a queue of a resource pool, and that's how you'll get the result. Static or rigid resource allocation between schedule, and again, we had the resource allocation between schedule and ad hoc jobs, but that was fairly static with some liberty of the dynamic pooling, but still there was a boundary around it. The third thing that was an issue with the interactive queries was short-lived or stateless context. Now again, while we could have one long-lived context, but then there was a risk of resource hogging. What would happen, or how would we do high availability for it? We created short-lived stateless context, but then there is an issue that when somebody is doing an interactive query, then it's almost like a session, because they might have done a query in previous step. They might have created a temp data view. They might want to create their own UDFs. How would you support all that into a very small set of short-lived context where you are doing multiplexing or you are spraying the queries on top of that? So these are all the challenges that we started with on interactive queries. On the storage side, though, we did some steps to optimize the interactive queries. For example, once we did data from Kafka and Scoop based on the data collections, we were able to put it on the tenant or event and even the time-based partitions that helped us in optimizing these queries, because now these were in a folder for an event and also time partition, so we were able to use them efficiently. We were able to read the data what is required. We also implemented time-based compaction to optimize the query for sparse data. Probably when we were doing this, Delta was not there. Now Delta would help us here. So we did the same compaction to compact the files on a running system and then then redirecting the queries onto this this compacted file. Summary profiles, we created summary profiles to reduce the number of joins. That was again an optimization to make the query more efficient. But after all this, while the individual query performance is optimized, but the problem of concurrency, where you have multiple queries running together, how to optimize that was still there, because these multiple queries need to contest for the common resource, and how to do a fair scheduling on top for that resource was still very much there. So just to summarize, so what was needed for our interactive query system to scale up? So we of course needed a SQL-like query tool for ad hoc analysis. That was not there in our phase one. Then scalability for concurrent user. They were expecting fair scheduling. They were expecting responsiveness. Because whether it's one query, one user, or whether it's 10 query, 20 users, they were expecting a fair scheduling and a proportional response time for their query. High availability was another thing. They were looking for that whenever they are filing the query, they should be able to get the response. Performance specifically for scans and joins. They were looking for how to make it more performant. And then extensibility. Extensibility means when they are running the query or when they are using the system, they should be able to use it just like any other ad hoc query system. They should be able to create their own views, their own data sets, their own UDFs, and use them independent of what other users are doing on the system. So this was the set of requirements where we said that we need to build something more in the ecosystem to enable these use cases. And for that, what we did as a first stage is we started the project Indicium, on which we did it in like 2 phases. First phase was to pull up some common components which are available in the ecosystems, how to combine them together to solve some of these problems. And then in second phase, we put a layer on top of it or logic on top of it to how to smartly allocate the resources between, between various users who are competing to execute their queries. Right, so that brings us to Indicium, and I'll just hand it over to Kapil here. Kapil was our primary architect for the Indicium project. Maybe Kapil can hand us the second part.
Thanks, Arvind. Hi, everyone. Good evening. So I'm Kapil. I've worked as a data architect building scalable compute and data platforms using technologies like Spark, of course, and Mesos and Docker. And coming back to Indicium, like we are almost halfway through the slide. And first, let's introduce what is Indicium. It's actually Latin for information, literally. So it's like any users who want to access information interactively, Indicium was the place to go. So let's look at the first phase where we took up some of those open source components. And we call it as managed context pool because we were managing a pool of Spark contexts. So this is how it looks like. Let's spend some time here. So we have, to begin with, we have Apache Zeppelin, which is an open source tool. It offers notebooks, just like IPython, Jupyter, or even Databricks notebooks, right? Then we have Spark Job Server. That's also, again, an open source component. It was originally built by Uyala, and it's currently under Spark Job Server's own repository. It offers long-lived contexts and allows users to remotely deploy their own custom applications and run different different commands on those applications remotely and access data through REST. Right. Then the context that we were running on Spark Job Server were SQL context, custom SQL context. They were running on Yarn, and they were accessing data through HDFS. To be more specific here, it's slightly unconventional setup for Apache Zeppelin, because usually what happens is Apache Zeppelin has a concept of interpreters. So when a user types in a query and fires it, there is an interpreter sitting behind the scenes which will interpret it, implement, execute the query and return the results back. So for instance, they have a out-of-the-box Spark interpreter which would have a Spark context running within Zeppelin itself. It will run the query, it will return the results back. However, what we did was we implemented our own custom interpreter, which would not do anything, which will simply pass on that query to the job server, which had REST APIs, and it will get the results from the job server and then return them transparently back to the user. Within the job server, we had a custom application, which would, of course, handle the user's queries, and we also had a custom SQL context. As Arvind mentioned, we were using an extension of the default Hive context that we have, and we'll get to that in more detail later. So here is some more details on the different configurations that we were using. We were using Apache Zeppelin 0.6. It's 2016 timeframe, right? And we had multiple interpreters and multiple notebooks, so that there were hundreds of users with hundreds of notebooks and around, say, tens of interpreters each handling multiple notebooks. On the job server side also, we had a fleet of job servers. So each, there will be multiple job servers, and each job server had multiple contexts themselves. This architecture itself solved a lot of problems for interactive querying. These were the features that were available out of the box. You have the visualization, you had the multi-user support, you had a familiar SQL-like querying interface. All of this comes with Zeppelin itself. By adding job server onto it, the first and foremost benefit we got was access control. So if you have the regular Spark interpreter in Zeppelin, any user could simply stop it. So if you have 20 or 100 of users using the same interpreter, and some of them have cached their data sets, or some of them have introduced more aliases onto it, Now, if one user stops the context, then the data is gone, right, for every one of them. So because we had a custom interpreter which would only expose a certain limited set of APIs, namely to run SQLs, to import some data, or to export data out of it, right? So that way we had some access control, so we'll not accidentally stop the contexts. Then we also had a custom SQL context. The basic idea was that in Spark, the way it usually works is that you have a data source, and you read that data source to create a data frame, and then you register it as a table name, right? So suppose you had a data source and a location S3 location, and then you read it, build a data frame, and then register it as, say, orders table. After that, you can run a query on this, select count star from orders table, right? However, what we did was slightly different. It was almost the other way around. It was that we extended the SQL context and intercepted a method to resolve the table name, right? So if I say select star from orders, it will say, okay, fine, I know that orders table is not defined yet, but I have an external service which will tell me where is the orders data lying, right? So I'll read it from there, build a data frame, and then return it back. This custom context also allowed for table wrappers, something like, as you can see, select count star from last X days of table. Now, in regular Spark SQL, it will be the last X days of table. Everything between the backticks will be treated as a table. However, with our custom interceptor, it will know that, okay, this is just a regex. I have to parse it. The original table is something else, and I have just to apply certain filters on top of it, which is to read just the last X days of data. That said, while it solved a lot of problems, it was far from being perfect. There were a lot of issues with it still. The biggest of them being, the Zeppelin interpreters were hardwired to a single job server and a context, right? So Zeppelin interpreters had a configuration which would say that, okay, I'm tied to this job server and this context. While we had a fleet of job servers and contexts, but if the one which you are tied to, if that fails, right, the context is killed somehow, or the Zeppelin or the job server itself crashes, right? So then there is no automated failure handling, right? And you cannot recover from it. Someone has to manually go and configure that interpreter again to another healthy context, right? This was not very helpful. Another problem which we had was load balancing, of course. That is, there was no automated way of identifying that whether there's a context which is getting hogged by a number of queries while the others are sitting idle. And last but not the least, there was also a problem with that the particular version which we were using with of job server, it was not very compatible. It was not very compatible with Spark 2.x, so it would only support 1.6. So with these problems, we came up with our own set of improvements and optimizations, which we call as the phase 2 of Indicium, and where we introduced something called a smart query scheduler. Let's have a look at the architecture for it. So as you can see, it's pretty much the same as before. It's the only new component here is the smart query scheduler. So what would happen is, earlier the user queries would go to Zeppelin, which will simply pass them to job server. Now instead, every query would first go to query scheduler. It will tell which job server instance and which context on that job server instance to run that query on. It will return that information to Zeppelin, and the interpreter will then pass on, just like the phase 1, to the job server instance and the context, right? So this, and meanwhile, the query scheduler would be monitoring the job server, the fleet of job server instances and the context for their load, for their health, and other things, right? So here is some further details on the configuration. By the time we built this, it was December 2016. Zeppelin 0.7 had come up, so it would support, on every notebook you can execute a statement, while previously it was only per interpreter. We also built our own custom fork for job server 0.7. At that time, still the 2.x was not fully supported, but we built our custom fork and added support for 2.x, which has a lot of improvements on data frames, right? And smart query scheduler, we'll go into more details of what all features were supported by this. And there were more other optimizations like monitoring and availability, right? So it will monitor how many jobs are running per context and which contexts or which job servers are available. So specifically on Smart Query Scheduler, these are the features that we added. So for the first thing was, of course, now the interpreter is agnostic of, so it does not even know where I would run the next query onto. It will practically go, every different query could go to to a different context every time. And it will allow for load balancing, and a couple of features which will also go into further details, like query classification or dynamic scaling, shared caching, and all that. We'll go through all of them actually one by one. So query classification, what does it mean? Basically, if suppose you have a number of queries which are very, very compute intensive, like say have hundreds of joins, or there are queries which are doing some export of data, right? So they would obviously naturally take a lot of time. while a user with this very simple query for reading just last 1 hour of data would not want to be bogged by this. So even though you are doing load balancing and everything, it's possible that a load balancing in its very naive form would be just a count of jobs that are running, right? But it would not identify what type of queries you're running. So we would have a custom heuristics to identify that, okay, the export queries, they can probably go to a single context or a separate set of contexts, while the interactive queries or the queries which will take less time can go to a different context where they can be served faster. Another thing which we introduced was, or added on top of it was Spark dynamic allocation, which actually Spark provides out of the box on Yarn, right? So what it does is that you can have a range between minimum and maximum number of executors that your context can span into, right, or run tasks on. And how it would help us is that usually the daytime there will be hundreds of users and thousands of queries that will be running. So the context will expand up to the maximum number of executors and take up a lot of memory and resources on the cluster. While in the night time, when your daily nightly jobs are running and the users have gone home, right? So the Indicium is mostly idle. So the cluster resources will be available for the nightly jobs, and the Indicium context will be reduced to the minimum capacity. Then we used Alluxio for as a common cache. Using Alluxio and not the Spark memory caching helped us in 2 ways. One was that it avoided the data replication, so that you do not have to cache the same data set or the common data sets that are being queried again and again into each of the contexts or on each of the job servers, but you had a common location, right? And it also made it fail-proof or failure-proof from executor failures or even the context failures, right? So even if a context fails, your data is safe because it's cached somewhere else. Then we also added, with the phase 2, we added support for persistent user views. What that means is that in the phase 1, you had an interpreter. It would be tied to a context. So if a user wants to register an alias for a query, then it would be registered on that query context itself, right? But the users which are querying against other contexts, they would not be able to see that alias, right? Now here, since every query was going via the query scheduler itself, so the query scheduler will make sure that a query which is trying to make an alias, it would register that alias onto all the contexts that are available, and it will make sure that if a context dies or quits and it comes back again, thus all the aliases are still available on every context. We also added support for TTLs, which is time to live, so that the alias would go away automatically after a certain time. Then another thing which we added was workspaces. So remember I mentioned that we had a custom context which would allow for that, okay, if I'm saying select star from orders, it would identify, okay, orders is a table name and I need to read the data from a certain location. But usually what happens is that over a period of time, you would not want always to read all the data. So we allowed for a concept of workspaces, which are custom catalogs. So what it would say is that the default catalog could say that I want to read only for last 90 days of data. Then you could have a custom catalog for saying I want to read just last 7 days of data or last hour of data. So that way you can define these configurations like custom time ranges or different sources of reading the data, or different caching mechanisms which could be defined globally, that is across the catalogs or per catalog or even per table within the catalog. Right. So here the idea is that while Indicium was a common interactive querying platform, the users were very, very different, right? So it would be that data scientists would want that, okay, I want to run my query on orders data, but I always want to run it on 90 days. While a sales management executive or a sales analyst may say that I want to run just last 7 days of data, but I don't want to specify all those filters every time, right? So they could both be working on different workspaces. And another thing was that you could have different time ranges for different tables, so that if you have a lookup table like inventory, now that could be the full table, while the behavioral data like just user clicks, they could be referred to just a smaller time range. And the last feature which we did in Indicium phase 2 was automated pool management, which was about again monitoring and recovery from it. So we had monitoring scripts to track and automatically restart unhealthy contexts or job servers. And we had APIs, provided APIs to start or stop the context on demand, or to even modify the query scheduler itself to update the heuristics, or to to register new context or new job servers on the fly. So all these things helped us to build a interactive querying solution which would not only come up with the features of interactive querying, but also scale and be robust enough to meet our demands. So that was about it. Thank you. Any questions?
All right, thank you. question on the analysis of the queries. So the queries or the complexity thereof drive where you sort of put your, to which node you schedule and so on.
Right.
How did you do that? Did you actually parse the SQL and did some sort of query plan analysis, or was it mostly based on heuristics, on historical data?
Yeah, so Spark itself gives a good capability of parsing. It has classes to parse SQL itself, right? So for instance, a query would, with say a cross join, I think in fact that was in, I think now cross joins are automatically not supported, right? So it I think gives a warning in 2.2 or something. But back then it was not, there was no such check. So users could accidentally do a join between two tables without specifying any condition, right? So it would be a cross join M cross N. So what we did was that we used the Spark parser to parse the query and identify that, okay, this is not right. So,
I have a question about this dynamic Spark context. Is this an actual Spark feature?
Yes, dynamic allocation, you mean,
and
right?
Is it running? It's basically running all the time, and you can dynamically at some point decide, okay, now you go up to max 300 cores?
Yes, so the way it would work is that you had a long-running context on job server, so it was running 24/7, but you would specify the range of minimum and maximum executors. So if there is no job running on it, and you will also specify initial number of executors, right? So suppose the min is 4 and maximum is 40, then it would have just 4 executors running. And if a user runs a query and my query scheduler points a query to the job server, runs a query on the job server on the context, then the number of executors will increase as per the tasks.
Without restarting the context?
Yes, without restarting the context. And it will also scale down.
It will scale down if it's not used for some time.
Yes, yes. So there's a time, and this feature has been available in 1.6 onwards as well.
Maybe just in Yarn, right?
Yes, yes.
Okay.
Hey guys, I'm not sure if you have mentioned, but were you guys using public clouds or your in-house infrastructure for doing this?
Actually, we were using both.
Okay.
We were on a public cloud initially for about 6 months, and then towards the start of this year, we moved onto our own data center and our own cloud.
Okay.
So on public cloud, we were using S3 as a storage, and here we are using HDFS.
So there was no S3 in your in-house data center?
No, in our in-house data center, we were using HDFS.
Okay. And one more question on Alluxio. So you were using only HDFS as a backend or some other storage as well beneath Alluxio layer?
No, there was no other storage layer on. So for Alluxio, we were using not even HDFS. It was just the SSD bit.
Okay.
SSD. Right.
All right, thanks.
Yeah.
One more. So did you consider using the Spark meta store for these permanent tables? Because I think you were persisting them in this smart query thingy. Couldn't you just use the meta store for table definitions, which should be long-lived?
Which tables you're referring to? It's
the views, I think you called them. A user defines a view and wants
views.
Wants it to be...
No, these views are typically, because what happens is when a data scientist or a data analyst is working, they might be creating a query, running a query, and then want to store that intermediate data, right? And they might be using it for subsequent 1 day, 5 days, 7 days, right? So these are like temporary data for them as well. This is a data which is they have computed based on a query they have created or find out a set of records on which they want to do further processing. Right, so these are the temporary views that they want to keep. But they should be available in their context because they will be firing more and more queries in the same context using those output of that query.
Actually,
so
that's why we had
Spark can always go and recompute it, but to optimize it, they would like to persist it, right?
Actually, that's why we had the concept of TTLs as well, right? Because they would not want these tables to live forever. They just wanted that, okay, for next 3 days or 4 days, I'm going to work on this data because I'm just say analyzing the last week of data, right?
Hey guys, one last question on infrastructure side. So when you moved from public cloud to your private cloud, you were using OpenStack or any other layer for compute? What was?
OpenStack.
OpenStack, wonderful.
All right.
All right, I think that's it for today. Thank you again, and a round of applause, please.